It really looks as though you're on a sailboat.
Mm.
So the next book that I am working on has a chapter on how sailboats work, and I think the answer is a bit different from what we all presume. And one reason for that is that if you guys in Scandinavia know about ice boats, right? And you know that ice boats can actually go almost directly into the apparent wind, maybe just 3 degrees off. And that doesn't make sense because if the wind is blowing on your face, you should be going backwards, um, but but you go forward. So this is an issue. I mean, how is it possible that if someone is pushing on you, you go in the direction of the push. You don't go in the opposite direction. So there's something that doesn't work with the current view. But anyway, that's a different subject. So,
But very exciting. And
uh,
are there any news about the publication?
I'm. Excuse me. Let me just open the door before we start because otherwise the cats will. I'm home. One moment.
What did you do?
I joined. Sorry.
No, you should not join. No, leave me.
Okay. Yeah.
Ellos tres y Pollack.
Hola.
David, maybe mute.
Hola.
Hola.
Sorry, it was me.
Español, no hay problema.
Sorry.
Hello.
Hello.
Good to
Hello.
see you. Yeah, we are here in Sweden.
Suffering from heat or not so bad?
Yeah.
No, we're happy in Sweden.
Yeah.
That was not my question. I know you're happy. It's good that somebody's happy in Sweden because I heard that a lot of people are depressed in Sweden.
That's when November month comes.
Oh, November. Yeah, I gotcha. Okay.
In the pandemic right now,
Yeah.
perhaps.
Yeah.
Well, I think it's, yeah.
Yeah, let's start.
Let's start. And since we are such a small audience, I think we can just take a quick round and say that here in Sweden we are 5 people who have hosted the water bridging camp in a few days here at World of Wisdom, and yeah, and we are excited to hear your talk, Jerry, and then I understand that we also have 2 guests calling in from Ibiza, so that's wonderful. So
Okay.
let's get started.
Okay. Welcome. Some of you have heard this or much of this message before. I'll assume not. And so I'd like to talk about a phase of water that we identified. I'd like to say sometimes it's a new phase of water, but there's nothing new about it because it's been around forever. What's new is maybe some identification of this kind of water. And what I'll be focusing on, I thought next slide is this one. Yeah, okay. I'll be focusing on light, and most people would be otherwise surprised that light and water could interact with one another. But this is one of the major themes that I will be dealing with. So I start with questions because I think a lot of people who are not so familiar with the topic, a lot of people will think, water, everybody knows everything there is to know about water. Everybody already knows it because water is so simple. It's all over the place and scientists have been studying it forever. Well, at least for many years. So you'd think that everything about water that you could know is already known. So I like to start by dispelling that notion. And let me show you a few slides, and I'll challenge you, those of you who've not seen the slides before, to give me an answer. And if you can't give me an answer, it means, well, you really don't know everything there is to know about water. So here's a simple one. And I think you can just look out and see it from where you are, approximately.
Yes.
You see it all the time, but how many of you really are thinking about what keeps the clouds suspended? So the cloud's made of water. And if you were to climb to the same height and take a pail of water and turn it over, the water would simply dump right down in one large bolus. But the cloud stays up there. It's water. So how is it possible, if water is pulled down to the earth by gravitation, how is it possible that the cloud sits up there in the sky and we see it every day? And how is it possible that you never even think to ask the question? Okay, I assume that you don't know the answer, although I think some of you may know the answer because you're my friends. Okay, here's another one. So why do clouds float? Here's a water bridge, which some of you are, I know, familiar about it. The person who developed it mostly is Elmar Fuchs, now in Holland at Wetsis. And we've repeated the experiment, and so have many people. And you take 2 beakers and you fill them near the rim and put them lip to lip. And then you put 1 electrode in one of them, 1 electrode in the other, and you connect it to high voltage. So you apply the high voltage, and here's what happens on the video. You get a bridge. That's not astonishing, but if you then move 1 beaker from the other beaker using a motor to do it, you can see that the bridge actually sustains itself, and it can sustain itself for up to 3 or 4 centimeters indefinitely. And it's actually almost so stiff looking because there's so little droop that you could practically walk across this bridge. And I think you've never seen, if you're not familiar with this, you've never really seen water behaving in a way like that, because your experience is not coincident with this kind of behavior. So tell me what's going on. And if you can't really explain what's going on here, then you don't know everything there is to know about water, because it's just water, basically. So that's the second one. So here's a third one. I love this one. This is a lizard who lives in Central America. And this lizard spends most of its time sitting on a tree branch. However, when stimulated or hungry, or I don't know exactly what, the lizard will jump from its tree branch and walk on water. And because it walks on water, it's often called the Jesus Christ lizard. This video is, I think, from National Geographic. And the question is, well, how is it possible walking on water? And if you don't know the answer to that, then you don't know everything there is to know about water. And finally, I like this one a lot. This is a demonstration from a Japanese scientist, Shogo Ueno from University of Tokyo. This was taken about a decade ago. And it looks very complicated, but it really isn't. This is a trough of water, and he put some red dye in it just for show. It's not necessary at all. And sitting behind that is a very strong superconducting magnet, and that's what Professor Ueno studies. And the interesting thing is, he turns on the magnet. As soon as he turns on the magnet, the Red Sea splits so that Moses could walk across it. So tell me, this is water. The red dye is irrelevant. You can remove the red dye, put green dye or no dye, and the behavior is exactly the same. So what's going on? Okay, so I've shown these 4 slides as a kind of introduction, just to kind of make you aware that not everything is known about water. And that it's really hardly the case. And in fact, water used to be a subject of intense study, but because of a few debacles that took place and a few embarrassments of prominent scientists studying water, a lot of scientists have stayed away from water. So it's just now that scientists are beginning to come back to studying it. For myself, my inspiration came from this guy, Gilbert Ling. Unfortunately, he passed and he almost reached 100 years. He ended a nursing home. And the first time I met Gilbert Ling, as I said, he's the inspiration. I had known something about his work, but somebody invited me to a conference and Gilbert was at the conference. And it was a conference to commemorate the life work of a Hungarian biophysicist. And this guy, the biophysicist, had been involved in two fields. And one of them was water, and the other was muscle contraction. And since I had been studying muscle contraction, I was invited to represent that field. And the guy whose life was commemorated didn't agree with the current views on muscle contraction, and I didn't agree either. And so I was to represent the unorthodox view of muscle contraction. But at this conference in Hungary was Gilbert Ling, who I'd heard of before, but I hadn't met, and also other scientists who had evidence to support Gilbert's point of view. So what was Gilbert's point of view? A really radical view. His idea was that inside the cell, the water inside the cell was not like water in this cup, which I just poured for drinking. In this cup of water, you know, liquid water, the molecules of liquid water are bouncing around at a fierce number of times per second, and they're all randomly oriented with one another. And Gilbert said, no, that's not the case. Inside the cells, inside your cells and my cells, the water molecules are lined up. They begin their lineup at the surface of the solids inside the cell, for example, the protein surfaces, nucleic acid surfaces, and then they build. It's sort of like soldiers at attention. And the cell is filled with this kind of water. Of course, if this is true, then the textbooks are wrong in so many ways because this water's physical properties differ so radically from any other. And Gilbert came, Gilbert was, I don't know to use the word distinguished because he was controversial more than distinguished. But by the time I met him, he'd written 4 or 5 books on the subject. But he came from a distinguished background. After World War II, the Chinese government decided to send some scholars to the US to study. And it was, I think, 1948 or 49 or something, that they looked around. The first cohort was chosen, and they chose a biologist, that was Gilbert, and a physicist and a chemist. And the physicist went on to win a Nobel Prize in physics. That's Yang. Yang was famous not only as a physicist, but also famous because at age, I think 85 or 90 or something like that, he married his translator, who was in her early 30s. And so there was more discussion in China about his marriage than there was about his physics. Anyway, Gilbert was one of the 3, and the rumors are that they thought that Gilbert was the cleverest of all 3. So Gilbert had a lot of radical ideas, and the water inside the cell was one of his most radical ones. I must say, I was really impressed when I went because the evidence that was presented by other people in favor of his idea was really impressive. So I went home excited. I gave one of his books to my students and postdocs to look at, just out of curiosity, to see what their responses would be. And they came back to me and they said, this is amazing. This guy's ideas, if true, they will turn biology upside down and maybe chemistry, and they look to be maybe true or almost true or something. This is really important stuff. Unfortunately, Gilbert's capacity for writing was not great. Gilbert had a tendency to write for himself and not for other people who were not deeply schooled in the physical chemistry of what might go on. This is really arcane physical chemistry, not easy to digest. So I decided, based on my own thoughts and based on the feedback I got from my students, that I need to do something about this. And what I decided to do was to write a book describing Gilbert Ling's ideas. And a book was published in 2001. It was called, or is still called, Cells, Gels, and the Engines of Life. And the first few chapters dealt with Gilbert Ling, but I went on beyond Gilbert Ling to discuss the really importance of what he called structured water. In other words, the water molecules are organized for biology. And one of the central points that I brought out, Gilbert didn't like this because he felt that I had gone beyond what I had intended to do. And I adduced evidence to suggest that everything the cell does essentially is triggered by a transition between what he called structured water, the one where the molecules are organized, to ordinary water. So you switch from one to the other and the cell gets activated. So for a muscle cell, it's a transition between the structured water and ordinary water that triggers the contraction. And for a nerve cell, the same thing triggers the signal transmission. And for a secretory cell, it triggers the secretion. So Gilbert was really unhappy, and we had some difficulties, and eventually they were worked out, but that's a side story. So the book, my idea was to popularize Gilbert Ling's point of view, because it seemed to me that he was on to truth, or something close to truth. And the book was received with mixed emotion, mixed response. Some reviews said, this is the biggest nonsense in the world. It's just a reflection of Gilbert Ling, and everybody knows that this guy is crazy and his points of view are nonsense, et cetera, et cetera. There you go. Thank you. Cells, Gels, and the Engines of Life. Thank you. It's got a very nice cover. Yeah, okay. Thanks for showing. And other people were really enthusiastic about it. One guy wrote, a guy who's professor at Harvard, a well-known guy. This is a 304-page preface to the future of cell biology. So there were two camps, one side, the other side. And of course, being a curious person, I really wanted to study this kind of water. We had no experience studying water. We had experience studying muscles. So I began in a pretty naive way. And the way it began was with Gilbert Ling's concept. So he said, inside the cell, you've got proteins, and then you've got water molecules. And these water molecules here are shown as dipoles, plus, minus. And they should stick to the charged surfaces of the proteins or nucleic acids or whatever. And the standard view from physical chemists is that you may have one or two layers of this ordered water, but soon, because of thermal motion or Brownian motion, the order will give way to chaos. And eventually you'll get, when you go far enough away from the surface, you get randomness. Gilbert said, the standard view is maybe there are two molecular layers that are ordered, one or two, maybe three. And Gilbert said numerous. He didn't specify what numerous might be, but the implication is maybe hundreds or thousands, certainly enough to encompass all the water inside the cell. So we began with this idea that you've got ordered, like a liquid crystal, you've got ordered water molecules, and crystals tend to exclude solutes and particles. So we're looking for an experimental setup where we could see a region somewhere where particles are excluded. It's as simple as that. And we had some hints. I won't go into it because it takes some time of an experimental preparation where we might see that. And it looks something like this, and we set it up in our lab. So this is a chamber that you see here, and in the chamber, we put a gel. The first experiment was polyvinyl alcohol gel, but we've repeated so many different gels with similar results. And then here's the boundary of the gel. Sorry, the video is not so clear. This is one of our first records. And then next to the gel in the chamber, we put water and particles. And the particles were little spheres called microspheres. And these are used very frequently. And we looked in the microscope, and immediately we could see a region where the microspheres seemed to be excluded. And we were excited because we thought, oh, you know, it's possible that this region next to the gel is a region where the water molecules are ordered. And because the molecules are ordered, they would exclude these particles. It's better seen on video because we were kind of surprised if we waited. This is over a period of about 3 or 4 minutes, or 5 minutes. It seems something is growing and pushing these microspheres away. And this region, as you can see here, is roughly 50 micrometers. That's like half the thickness of one of your hairs. Mine too, if there are any left. And we began seeing this again and again and again, that something at different gel surfaces would then push these little particles away, and they would stay away essentially indefinitely, or at least a few days. So someone said, gee, you know, you ought to give this a name because people are talking about it. And so an Australian colleague said, well, you should call it exclusion zone because this is a zone that excludes. And the water inside here would then be easy water. It's easy to remember. The problem is in Europe, it's EZ to remember, not easy to remember. So it doesn't work as well as you know, as you might think. But anyway, we began calling it easy water, and later, because we learned a lot more about this water, we called it fourth phase water, a different kind of water, maybe slightly or somewhat different from what Gilbert Ling had suggested, actually a lot different, but somehow ordered. Okay, so there we were. Whoops, I didn't mean to do that. Okay, so in terms of the generality of this, I'm not going to show you a lot of slides because there are other things to tell you. We learned by doing many experiments that many surfaces, many hydrophilic surfaces, that is surfaces with charges or molecules with surface charges, hydrophilic meaning, you know, if you drop water on the surface, it spreads out, as opposed to Teflon, where if you drop water, it beads up. So we found that not all, but many hydrophilic surfaces generate exclusion zones, and many solids are excluded, ranging from these big spheres, microspheres, microns in diameter, even larger particles are excluded, and all the way down to molecules the size of, actually, we found that even ordinary water is excluded from the exclusion zone, and also some salt. So it's very general phenomenon. Now, so your question, if you haven't fallen asleep yet, question is this water really different from ordinary bulk water? I've alluded to the possibility that it might be different because it pushes out all kinds of solutes, but I've shown you no direct evidence. And so this is the evidence as of about 8 or 9 years ago. Evidence that exclusion zone water is physically different from bulk water. And most of it's been published. And so I don't want to spend the time going through, but you can just sort of glance at the kinds of evidence that we produced and that has been published. And anybody who's interested certainly could go to it. But I do want to focus on one of these just to give you a sample, and because it's really important. The EZ water has a negative charge. And we we determined that by direct measurement using micro electrodes, very tiny, sharp-tipped electrodes, in fact, invented by one Gilbert Ling. Surprise. He should have won a Nobel Prize for that, but other people used his technique to win Nobel Prizes. Anyway, we use these fine tapered electrodes, and we could see that typically the exclusion zone has negative charge. Just by sticking electrodes in and measuring potential difference between that zone and some remote zone. So let me just talk about that one for a moment. And so because this zone is typically negatively charged, so this is some material, and here's the surface, and this is water, and the idea is that the exclusion zone, as I said, typically is negatively charged, and the region beyond is actually positively charged, equally positive charged. So you have a kind of battery that's here. And how do you get a battery? And why is this occurring? Just for shorthand, it starts with the water molecule, because when everything starts here, even before this zone builds, it's just water. You just take some water and pour it into a chamber next to one of these surfaces, and things start to happen. So what happens? Well, you're starting with water molecules, and the water molecule looks like this, with the oxygen negatively charged and the hydrogens positively charged. And what happens is in the water that there's a cleavage that occurs. It occurs right here through some energy that comes in, and I'll address that in a moment. And the water molecule splits. And so this part of the split contains oxygen and hydrogen, -2 and +1. So usually this one has one net negative charge. And after this is split, you might call it a dipole, it sticks to the surface, and you get a net negative charge. And meanwhile, the positive charge gets cast out here and sits in the ordinary water. So many of these start building one upon another, and you gradually get these negative charges to build up, and you have a zone, which is what we call the exclusion zone, or fourth phase water. So the real structure, I'm not going to talk to you about the development. You can look in my fourth phase book. Do you have that with you to show? Doesn't matter. I'll show a picture. Wow, you guys are amazing. Yeah, I'll show a picture of it at the end. So you have, oh, thank you. Okay, that's great. Thank you so much.
You need any page? We can.
No. I've got the slides. It's okay.
Okay.
Just your smiling faces are wonderful. Okay, that's great. Okay, so you've got the material sitting next to water, and the real structure, which we deduced from a lot of evidence, and I'm not prepared to go through the development because it's going to take too much time, and I want to talk about some other stuff. But you'll see it in the book, for example. And it's a sheet-like structure. It's not like individual water molecules, dipoles that are lined up. It's a sheet-like structure, and it builds one sheet at a time. And each sheet is a honeycomb. You can see all the hexagons that you see, and it builds from the water. So you start with material and water, and you get these sheets that build first the first one, the second one, the third one, and then after the fourth and fifth, you got another, you get another one that builds and another one that builds, and they just keep building. And they can build many layers from the water. These structures build. And these are the easy layers, or fourth phase water, or whatever you want to call it, or whatever you don't want to call it. And that's how it builds. And if you were to look at one layer, it looks like this. You can see the hexagonal motif that I mentioned. And of course, it consists of oxygens and hydrogen in this honeycomb fashion. And if you actually count the number of oxygens and hydrogens, it's not H2O anymore. It's actually something different. Actually, you might say, call it a chemical change. It's actually H3O2. And that's by counting number of oxygens and hydrogens in one unit cell. This is the chemical formula that you wind up with. And it makes sense because H2O is neutral, and we know that these layers are not neutral. The layers have negative charge. And so this one has negative charge because it would be neutral if you were to have H4O2. Then it would be neutral, just like 2 times H2O, but it's not. It's missing a positive charge, so it has net negativity to it. So now what about inside your cells? So your cells are really crowded. My cells are crowded too. And I think your cells are equally crowded, but you probably have more water because you're better hydrated. As you begin to get wrinkles on your face, you're less well hydrated, which means you got less water inside the cell. But what kind of water do you have inside the cell? So the cell is really crowded. It's crowded with solids, 70% roughly of which are proteins. So these are, let's say, mostly proteins, some nucleic acids. And this schema here, it doesn't really show how crowded the cell really is. It's much more crowded than, but you can get the idea. So you have proteins, and most of the protein surface is hydrophilic. There are some hydrophobic pockets. And the water that's next to it, therefore, should build into EZ water because these are hydrophilic surfaces. And measurements have shown that the cell is actually filled with EZ water. And one thing that you will notice is that EZ water has negative charge. So that means if you take an electrode, a microelectrode, and stick it into the cell, you'll measure negative charge because the water is full of negative charge. And I've written a paper suggesting, more than just suggesting, that the reason the cell is negatively charged has nothing to do with membrane pumps or channels. It has to do with the water that's inside the cell. So if your cell is functioning properly, it should have a lot of EZ water and a lot of negative charge. And if you're dehydrated, if you don't have enough, you have less of this water, less negative charge, and your cell is pathological or at least dysfunctional. And there's a lot of evidence for that, which I don't have time to talk about. I'll just say that cancer cells, for example, instead of -60 or -70 millivolts compared to the outside, is only -10 or -20. Same with pathological kidney cells. Now I want to address an issue that maybe is controversial, depending on where you're coming from, and that is, could EZ water contain memory or information? So you're all familiar with this. You know, you stick it in your laptop and it's got memory, it's got information inside. And so actually what's inside here and how is this relevant to water? So what's inside here, typically, not always, silicon atoms, and the atoms are organized in a regular array, not only in 2 dimensions, but in 3 dimensions. And each one of these can be addressed, and they have 2 different states. One is like a 0, and one is like a 1. And that's how the information is stored. So this one could be a 0, 1, 1, 0, etc. And as you know, you can pack a lot of these silicon molecules into a small space, and you have a lot of information. So why am I showing this, and how is water any different? Well, if you look at EZ water, it's actually very similar. So I've shown you the structure of EZ water, and the red ones here are the oxygens, and the hydrogens are in between. And if you focus on the oxygens, which I think are probably more relevant, more interesting, you can see that they're arrayed in 3 dimensions in a regular order. They don't flop around and bounce around rapidly a huge number of times per second. They're more or less stable, as is the case in crystals. So it turns out, I mean, the question you might ask is, well, okay, so we've got regularity here, but the silicon is arranged in such a way that it can have 2 different states, like a 0 and 1. What about this stuff? Well, it turns out that the oxygens have not 2 states, but actually 5 different oxidation states. You can check this in any chemistry book. And the one that's most familiar is -2, taken as the so-called valence. But there's also, besides -2, there's -1, 0, +1, +2. So there are 5 different states. Now, if this really can serve as memory, the same way as this can serve as memory, then the potential memory density, we calculated once, it's something like, I think it was close to 1 billion times the memory density of an ordinary silicon memory. So this has, if it works, and there's some hint that it might work, this should have a memory capacity that far exceeds anything that technology has ever produced. This is natural stuff. It fills your cells. It's inside your body. And it means that potentially your body has the capacity to receive and send information. And I know this is controversial. However, at our water conference that occurs almost every year, we're now, because of COVID-19, we've delayed our fall conference. But people report all kinds of interesting experiments that demonstrate water memory. So it seems like one of these weird topics, but if you examine the evidence, there's an increasing amount of evidence, and most people at this conference take it as a fact that somehow water can store information and memory. And I don't have time to go over all the experiments, but let me just show one or two slides. The one that's most well known, although not scientific, and that is the work of the late Masaru Emoto, who died 5 years ago, and his work is being carried on. And I'm well connected to the people in the group, and some of you may know that he did studies. They're not, as he says or said, he's a spiritualist. He's not a scientist, and therefore his treatment of data is a bit different from what scientists would do. And many scientists are highly skeptical. However, there may be something to it. And what he demonstrated, for those people who are not so familiar, is if you take a beaker of water, and you play a Mozart symphony, and then you freeze the water, you can get really nice crystal. And if you play John Lennon, Imagine, you also get a nice crystal. And if you think to the water, think about peace or thank you, focus your intention on it, again, you get beautiful crystals. And scientists object because these were not chosen randomly. They were some of the better crystals that emerged. So this needs to be repeated in a more scientific way. But on the other hand, if you use, I think this means you fool or something like this in Spanish, you get ugly crystals, and heavy metal music again. So the main point is that experiments like this have been repeated many times now by scientists who report consistently that water contains information or memory, and it's possible that where is this memory stored? I think it's possible that this memory is actually in EZ water, because ordinary water has no such capacity because the molecules are bouncing around and they're randomly oriented, and there's nothing stable to contain memory. But EZ water, there certainly is. It's a crystal. So the original question I asked in this first part of the talk, is the EZ water really physically distinct from bulk water? And the answer is yes. I haven't gone over all the evidence, but I've kind of presented places where you can go and check the evidence for yourself. It's a layered honeycomb structure, the best that we could deduce. It's not individual water molecules lining up, but this layered honeycomb structure with information storage capability, which is, I think, very important for the future. And it might respond to intention. So if someone is standing near you and kind of thinking loving thoughts, you may feel this kind of information transmission. Okay, so I mentioned this was like a battery, and you guys have cell phones. I'm the only one who doesn't. Maybe in the world, I don't know. And it's got a battery, and you know, if you want to charge the battery, you need some energy, and so you got to plug in, otherwise your cell phone won't work. So what about this water battery? You know, there's no obvious way that you can plug it into the 220 volts or 120 in the receptacle. So where does the energy come from? Otherwise, the battery will run down. And it turns out the answer is from light or incident radiant energy. How did we find out? Not by any stroke of brilliance from the investigators, but by some student who was doing what he was not supposed to do. And I've had a lot of young undergraduate students, you know, you give them a project and they go into the lab and they sometimes do it, sometimes they do what they like to do. This guy was doing what he liked to do. And he called me over and he said, hey, look at this. So what is this? This is real data here, one of our first experiments and such. And obviously this is drawing by my artist son. This is a piece of naphthalene, a hydrophilic material that we tend to use it a lot, although we've used probably dozens of different surfaces, if not more. But naphthalene, it's really easy to use. And this is actually a cylindrical piece, a tube of naphthalene that runs along here. But we were looking outside of the naphthalene, and or he was, and here is an exclusion zone, and the dark are the microspheres, and you can see, you know, after it was set up for 5 or 10 minutes, you can see a fairly linear boundary between the exclusion zone and the microspheres, and that boundary would ordinarily extend all the way across to here. But he took the lamp, this was a gooseneck lamp sitting right next to the chamber, and he put it up here somewhere, and he shined the light. And where he was shining the light, the exclusion zone, when I came, he showed me, it expanded just like this. And of course, I was flabbergasted by this. I didn't expect, because it looked as though the energy from the light, the photons coming from the light, were responsible somehow for building the exclusion zone. You know, it didn't take a rocket scientist to figure that out. So I told the student, take it away and see what happens. And sure enough, he took it away. And in a matter of tens of minutes, this receded back to the original. So this is reversible. But it's built by light, you see. And so, of course, this was a student experiment, and we wanted to find out which wavelengths of light were the most important, because, you know, the optical spectrum extends from blue to red, and then there's light beyond the spectrum that we could see, the UV region and infrared region. And so, and we found in these experiments, published experiments, that infrared light was the most effective. And what a lot of people are confused by what's infrared like. We can't see it. The wavelengths are beyond the red. You know, we can see typically from violet through red, but beyond the red wave, beyond these long wavelengths, we can't see. However, it's actually, it turns out the infrared is all over the place. We think of infrared, we think of, you know, if you turn on the toaster and you look inside the toaster, you see the coils that are glowing bright orange, and you can feel the heat. And you say, oh, well, you know, it's glowing and it's heat, so there must be infrared coming from those coils. And it's true. And the same thing with your electric range. But it turns out that everything is generating infrared. And so if you, for example, were to take an infrared camera, that is a camera just like your cell phone camera, but the sensor is sensitive to infrared wavelengths, not visible wavelengths, you get a beautiful image. And it's used at night where, you know, if you turn off all the lights, you can't see anything, but the infrared sensor will pick up infrared energy coming from everything. And so you can imagine it's useful for military purposes, but it's everywhere. And because it's everywhere, it means that since this is the stuff that builds easy water, it means that easy water is everywhere. See, so you have a situation that kind of looks like this in our environment, not just inside our body, but outside our body too, where you have a hydrophilic material sitting next to water, and you will always have some easy water because there's always infrared energy around. Should you decide to add more infrared energy, then the exclusion zone will grow. And if you take it away, you go back to the original default amount of easy water. So that's basically what we're talking about charging. So the energy for buildup of easy, or at least one energy that we know about. There may be more that we don't know about. And it's powered by light, by photonic energy, and which orders the water and basically charges the water battery. So the situation looks like this, something like the place where you are right now. I like to think of Hawaii as another place. Basically, sit in the sun. And if sit in the sun, you get energy. So the so-called water battery gets charged by sunlight. And as you know, roughly half of the solar radiation is in the infrared range. So it's ultimately the sun that supplies the energy to build the easy water you see here. Now, if you think that well, gee, you know, if it's getting you getting energy just by sitting in the light, can you harvest this energy in some way? Can you grab it and use it? And we wondered at first about it, and the answer is going to be yes. I'll show you in a moment. And here's one example that demonstrates that the energy can be harvested. And this is another undergraduate student who was doing what he was not supposed to do. So we, excuse me, we had just determined, excuse me, one moment. We had just determined that naphthalene, which we like to use, could also come in cylinders. And we wondered whether the cylinder of naphthalene showed the same features as a sheet of naphthalene. So I gave Arthur the task of checking out, taking the tube of naphthalene, putting it in water with some particles in the water, and seeing if you can get an exclusion zone on the outside and maybe even the inside, because we expected that might be the case. And he quickly determined that he could do that. But he started some other experiments, and I didn't know what he was doing. And one day I was sitting in my office, and Arthur came in, and you know, usually he's a Chinese student, and most of the Chinese students are polite. And you know, he barged in. I was sitting with someone who I think was an important visitor, but I can't remember who the visitor was, so maybe the visitor was not so important. And Arthur came barging in, and he said, you know, I saw something that looks like it might be interesting. I wanted to tell you about it, you know, so I'm thinking, okay, Arthur, you know, I got a visitor here. We're talking about, quote, important, unquote stuff. And I didn't say that to him. And so he started telling me, he said, well, what, I asked, what is it that you found? He said, well, you know, I've got the cylinder sitting here in water with the particles, and I'm using a microscope. The lens is here looking up into this. And what I see is something unusual. I see that the water is flowing through the tube and it never stops. And he said, you know, I thought this could be significant. And I'm thinking, if this guy is right, it's more than just significant, it's amazing because you can't get something for nothing. And I'm thinking, if he's right, and by the way, we checked to see, and he was indeed right about this. You know, usually, to drive fluid through a tube, sort of like your heart driving fluid through your vessels, you need pressure. Somehow pressure, you put pressure here and it goes through, but there's no pressure difference between here and here. These two are sitting at the same height with the water above, so there's no pressure gradient there to drive it. So it's got to be some kind of energy. Otherwise, this is work. You need work in order to push fluid through a tube. So where does the energy come from? And so I was excited because I was thinking, you know, this is the ultimate demonstration that what we saw in the laboratory, where we put extra energy from light, it was being absorbed by the water, and then converted into some kind of mechanical energy. So the water was actually might be acting like a transducer that actually took the optical energy and transduced it into mechanical energy. And we thought, this is really cool. And so it turned out that was indeed the case. And the way it works, it looks like this. So you take a piece of tubing, you put water in, make sure there are no bubbles, and then you immerse it into the water below with microspheres, and take some to the microscope. We use green light here to minimize the illumination. Look inside, and here's what you see. Whoops, I meant the next, yeah, here's what you see. So Naphion, exclusion zone, and the water flows, and it just keeps going. And we've had this going in the laboratory. We've had it going for a day and a half without stopping. And we know how to make it last longer. It's a technical issue. So we're excited about this, and various people coming into the lab saying, yeah, it looks pretty interesting, but you know, maybe this is a weird property of Naphion that we don't know about. Show us if this is more general. So we looked for some other tubular materials like Naphion, and it's hard to find. You know, thin, narrow tubes like this made of hydrophilic material. So basically, we built our own. How did we build our own? We took a gel, and we stuck a wire inside. And as it was gelling, we pulled the wire out. And so we had a chunk of gel with a tunnel that ran through it, little chunk. We take that little piece of gel with the tunnel, immerse it into a bath of water and microspheres, just like this situation. Whoops. And this is what it looks like. So this is in this case, a polyacrylic acid gel. Here's the gel. Here's the gel. And this is the tunnel. And, you know, in this case, is photographed after we'd immersed the chunk of gel in the water plus microspheres. So what happens? Well, the first thing that happens is the EZ builds from this surface and builds from this surface and pushes all the microspheres to the center. And the question that was asked, well, do you get flow? And indeed, you get flow, just like the Naphion tube. And we've now repeated and published it in half dozen different gels. The result is the same, except the speed is different, the EZ size is different, et cetera, et cetera. So someone else, we listened to people, someone else came and said, hey, you think this is run by light? Why don't you just crank up the light and see if it goes faster? So we did that, and whoops, I keep hitting the wrong arrows. And we published, just by cranking up the light, the speed can increase by up to 5 times. So this is really, this process is indeed run by light. And so it basically, we've demonstrated a kind of transducer where you have light input and mechanical energy output. So this is summarized in this slide. We have a hollow tube sitting in the water. Flow keeps going through it. And work is done, right, because you can't, the water has viscosity. And in order to push it through the tube, you need something, some energy to do it. Energy is required for any kind of work that you do or I do or anybody does. And the energy appears to come from what I showed you before, absorption from the environment to the water, especially the infrared energy, unless someone can identify another source of energy. So we think that's where the energy is coming from to power all of this, energy from the outside. And so basically, the conclusion is that water is a transducer of light energy into mechanical energy, and also, I haven't shown, but electrical energy. So water is a transducer of energy. Question is, do you, having water inside your body, do you use radiant energy? Well, you know the plants do, but you never think of yourself as doing that. You may want to escape Sweden to go south in the winter to enjoy the sun's energy, but do you actually use radiant energy or light energy? And so your Mother Nature, picture yourself as, mother, I'm not sure if that's what you really look like or not, but anyway, there's Mother Nature. In her wisdom, she doesn't look wise here, but let's assume that she's wise. And Mother Nature is saying, well, gee, you know, I've been pretty successful with green plants and some bacteria using light, photosynthesis, using light energy to produce all kinds of energy. And now I decided, well, I'm going to invent animals over and above plants. And, you know, animals can move around, they can forage, they can get their food, but what do I do about this light energy business? I've been successful with it in the past. I got two choices. I can either throw it away and start completely new, or I can keep it in reserve, you know, to use it maybe as a supplement to the energy you get from food, or maybe use it on a regular basis or whatever. So being wise and being conservative, I would guess that Mother Nature might have chosen to retain this mechanism in some way, this light mechanism, implying that you might use light and I might use light in ways that we hadn't thought. We receive light energy all the time. I apologize for this ugly guy. I think I got it originally from the internet and should have let my artist son redo it. Yeah, so anyway, you receive a lot, and the question is, well, either you can just re-radiate it out, or you can actually use this light energy in the same way that I've described. And so we're thinking, well, you know, it could be that maybe we use it. And one idea, since I actually started my career studying the cardiac muscle and also the circulatory system, thinking that, okay, one possible way that you could use energy is in the cardiovascular system, because, you know, you have capillaries that are sitting near the surface and some of the radiant energy gets in beneath your skin. Is it possible, I thought, is it possible that you can actually make use of this energy in helping your cardiovascular system? Of course, you know, nobody thinks about that, and I would not have thought about it until, frankly, I went to Russia. And whoops, okay, I'll go back. And I went to Russia to visit my friend Vladimir Vyakov at Moscow University, and Vladimir introduced me to his colleague in the laboratory next door, whose English was halting, so everything had to be translated. And the guy was telling me, he said, there's a big problem in the cardiovascular system. And I had my nose up in the air because I thought I knew something about the cardiovascular system, and I thought we really understood everything there is to know about pressure and flow and whatever. And I said, what's this guy going to tell me that I don't already know? It took 5 minutes, no more than 5 minutes, for this guy to convince me that I was all wet, that everything I knew or thought I knew was wrong. So what did he tell me? He said, here's the problem. He said, you know, capillaries are small. In healthy young adults, the capillary diameter can be down to 3 or 4 micrometers. And the red cells that need to pass through are twice the diameter. They're 6 or 7 micrometers. So you got a plumbing problem. You know, you try to push these gigantic red blood cells through a narrow vessel, and you know, they don't want to go. It takes a lot of energy to do it. And you can see from here the kind of squeeze. So this is a piece of muscle tissue, and this is a capillary, and here's another one and another one. And you can see that in order for the red blood cells to get through, they're squeezed. Ordinarily, they should look like this, but actually when they flow through, they look like this. So what does that mean? It means you got to squeeze them in order to get through. And squeezing them requires energy. So the Russians calculated, they like to calculated that if the heart were responsible for doing all this work, the heart would need to develop a pressure that's something like 1 million times more than even those with high blood pressure. So even if he's off by a few orders of magnitude, still there's a serious problem, and that is there's not enough energy to do all this work. The heart alone can't do it because it would need to develop a huge, huge pressure. So something else must be going on to drive the blood flow through the capillaries. And what is that? Well, after I left the laboratory, after all the vodka, my brain began to awaken again, and I'm thinking, boy, you know, we saw something in the laboratory. We saw in tubes, looks just like capillaries. There's this spontaneous flow that occurs powered by light. And I thought, oh, boy, is it possible that the same thing is going on in the capillaries, that you are actually, and I, are actually taking in light, and the light is powering this so-called spontaneous flow in the capillaries. It's something that maybe augments the power of the heart. And of course, we're excited about this. And so, you know, the question is, we knew about this issue in the laboratory. Radiant energy, might radiant energy help drive blood flow? And it's something that, you know, we would never have thought of had we not done those experiments. I don't think anybody would have thought about this crazy idea. So, and my student was very conscientious. He looked in the literature, and it turns out that a paper was just published a few years earlier. It was a study in mice. It was done by some Israeli group, and they were studying flow not in humans but in mice. And I don't remember exactly the experiment they did, but they had open chest mice, and they were measuring flow using a technique called optical coherence tomography. It's a fairly optically advanced technique that has very good resolution. And they were using that. And so after the experiment was over, they sacrificed the mice, and they sacrificed the mouse by clamping the aorta, and the mouse was very compliant, died within 10 seconds. And what they found is that, you know, they still had the sensor working that measured the blood flow, and the blood flow continued. It's supposed to stop, you know, the heart stops, the flow stops, but these guys found that it continued for 1 hour, more than 1 hour after death. Imagine, you got blood flow after the mouse is dead. They repeated the experiments, 10 different mice, they got the same result. Dead mice, effectively, depending on how you define dead, with blood flow. And my student actually did more research, and he found that over the past century, there are actually something like a half dozen papers produced that show the same thing in different animals, different ways of looking at it. So something is going on. There really can be flow after death, which gives you pause to think about what's the definition of death. So we decided to do some experiments to check this out, to see whether this mechanism that we found in the lab is actually operating even after death, even if after the heart stops. So we used a chick embryo, and so this is a mammalian preparation, 3-day-old embryo. And 3 days old means that the nerves haven't really developed very much, and the hormones haven't developed, so it's a rather pure preparation. So here's the eggshell, and Lee removed the top of the eggshell, and then could look with his microscope at different regions. This is the developing cardiovascular system with the heart here, and I don't know if you can see it, but there is a vessel here and the vessel here, and he could focus on either one of those two. And first question was, if you stop the heart, does the flow continue? And the answer was yes. He could stop the heart by dripping potassium chloride or injecting it in the heart, and right away the heart stops, but the flow continues. So here's one record. Actually, it's the sum of some record. This is flow versus time, and here he injected the potassium chloride, so the heart stopped, and the flow goes way down to some low value, but it's not zero. It continues at this value. And then he wanted to test to see whether the mechanism that we had seen in the laboratory was operative here. And the signature feature is that if you add infrared, the flow speeds up. So he added infrared starting here. And you can see that the flow sped up by a factor of like 3 times or something like that. And then he turned off the infrared and went back to the control value. So it looks as though, I mean, there's no doubt that the flow continues. And since the signature feature of our laboratory mechanism is confirmed here, it looks like that feature is actually working. And if it's working in your cardiovascular system and in my cardiovascular system. That is that we're using light, or I should say infrared light, that comes either from the outside or the inside from metabolism to help drive blood flow. So it's not your heart alone that's propelling your blood flow, but the vessels themselves are also propelling it. So I'm not suggesting that you actually photosynthesize just like plants, but I am suggesting that you do use something that's very similar to the first step of photosynthesis, which is the absorption of light. And the first step actually is that when light's absorbed, the water breaks into minus and plus. That's the acknowledged first step in photosynthesis. And it's the same as we discovered, not in photosynthesis, but in other situations. So we think that that first step is generic. It's not just in photosynthesis, although photosynthesis is one good example of it, but it's more generic than that. So where do we get our energy? Well, you know that you enjoy the food to get your energy, that's clear. But I think Mother Nature made the decision that we also use light energy. And one example of that, besides many other examples that I don't have time to talk about, but is that it's absorbed by the water inside your body. It builds EZs, which give you energy because EZs, charge is separated, and that's potential energy. And so it does that to your body, and it does that not only in the cardiovascular system, but the evidence implies that it's doing this all over your body. You have EZs in every cell in your body, and if you absorb infrared energy, that's one way of building your full complement of EZ water, which you need for good function. So when you go south in January to absorb more sun, there's rationale behind it. And I want to end with some practical applications that we've been working on. One of them is getting energy from water and sunlight. So you've seen this one before, and you can imagine how this could work. You put one electrode here, and it's like a battery, and you should be able to light a light bulb, and we can. And so what you see here, I'll show the video in a moment. This is, I think, a dozen or so cells with Nafion and electrode pairs in just the right place to capture this plus and minus. What? Hello? Oh, I thought someone was saying something. This is a switch. I need 5 more minutes, I think. This is a switch, and here is a magnifier with an LED underneath. And so what you're going to see now is that the switch is flipped and the light goes on. So it really does work. This is getting energy from water and ambient energy that's around us. So this is one potentially interesting practical application. Another is filtration, which we've actually worked on somewhat. And the principle is shown here. This is a Nafion tube. And you can imagine flow into the tube. And this flow is not just water, but it's got all kinds of junk. You know, pharmaceuticals, chemicals, you name it. And as sample junk, we use microspheres just to test the system. They could be highly poisonous too, depending on what you have. So when we have flow inside the tube, remember you get an exclusion zone here and you get an exclusion zone here, and all the junk gets pushed away from these surfaces and gets pushed to the center. And we developed so-called differential extractor, which is a very simple device with a fancy name. It just got two concentric tubes. And in the central one, what happens is that flow goes right through and gets collected, and you can see all the junk, all the microspheres here. But in the peripheral tube, this is EZ water. It's exclusion zone. It's devoid of all this stuff, and so you have very few here. And we've been able to achieve 200 to 1 separation in one pass in the laboratory. And we started to work. We have a startup company to make this available, and we spent some time working on it. We've reached some level of technical improvement, especially the throughput, which we've increased by many times, because this is so small that this throughput is the amount of good water that you get, or filtered water, is enough to satisfy the thirst of a flea, basically. But we've improved it. And so we also had been considering, this is suspended for the moment for some technical reasons, the idea is, can we separate salt? And we have some evidence that salt should be separable. And the idea, and we had some positive results and some not so positive results. And we're working on this. If it works, it means that you can put ocean water here and you get drinking water out of here. And there's no physical filter. The filtration occurs by virtue of the energy from the environment, which performs this kind of separation. So where you need water the most, like Middle East, for example, there's plenty of sunshine to power all of this stuff, but there's no water. There's plenty of ocean water, but no drinking water. So this could be really powerful. Okay, so conclusions. I guess the main conclusion is that we grow up thinking that water has 3 phases: ice, liquid water, and vapor. And we found that there's a 4th phase of water where the molecules are organized. And those of you who know the structure of ice and have just seen this structure will appreciate that the structures are not too different from one another. And that's why I put this one right next to the ice. It's different, but not so different. And it turns out, we have experiments published, that if you want to freeze water to go from here to here, you cannot go directly from here to here. You must go through this phase. So what happens is that water, you reduce the temperature, EZ builds, and it's the EZ that converts to ice. And if you want to melt the ice, you take the ice, it converts to EZ, which then converts to water. And that, I think, is why some cultures use ice melt to drink, because it's full of EZ water. And if you drink EZ water, you should be filling your cells with EZ water, which should be good for your health. So that's why the EZ, the 4th phase, is put here between the ice and the liquid water. And this has broad implications. I guess the central implication is that the water is always absorbing radiant energy from the environment and using that radiant energy, or the infrared energy. And one way is in biology. I gave you an example of blood flow. The evidence is suggesting that your blood flow is occurring not only because of your heart, but because of what goes on in your vessels. So this is just one application, but it's throughout biology. Whoops. in chemistry. So you've all read the chemistry books. I've read the chemistry books, and sometimes it's not so easy to understand the interpretation of the experiments. And nowhere in the chemistry book will you find an EZ that is present. Nowhere will you find charge separation. Nowhere will you find the effect of light. So if what I presented to you is correct, it means that a lot of the interpretations of what you read in the chemistry book will differ from the interpretations that are now presented. In other words, the books will change if what I presented is correct. In terms of weather, and my new book that I'm working on spends 3 chapters on weather, I think weather is a lot different from what you think. So if you listen to the weather forecaster, she or he will tell you that the atmosphere or barometric pressure is such, it's rising or falling, and the temperature is such, and therefore we predict tomorrow that you better take an umbrella to work with 50% probability. So, it might rain, it might not. Never have I heard from any of these meteorologists or atmospheric scientists anything about charge. Clouds are full of charge. And the reason, I'll just tell you without presenting the evidence, is clouds are negatively charged and the Earth is negatively charged, and that's why the clouds stay up. There's a lot about weather that people don't think about or talk about, and I think that if you take into account the fact that clouds are charged, of course you know that thunderclouds are charged, but it turns out all clouds are charged, and the evidence is there, but just ignored. I think this will have a very important impact on weather, and clouds are just filled with easy water, but that's coming. For health, you need easy water in your cells. Your body is filled with easy water. If you don't have enough of it, like is the case for me, I need to keep drinking to preserve whatever health is left. You need to drink a lot of water. Water is critical for health. If you're dehydrated, you don't function. In terms of food, if you'd like to preserve food by dehydrating or freeze food, it's nice to know something about the processes that are involved. For practical applications, I presented to you the prospect of filtration without a physical filter. It's called filterless filter. It might be usable for desalination. We're still not sure, but working toward that goal. If we could do that, this would be amazing for humanity. And also getting electricity from sunlight, using water as a transducer. I think this will be coming in the future. So there are many, 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 many implications. And before I sign off, I just want to mention something that is, in a sense, completely unrelated, but yet subtly related to what I've been presenting. And this is an institute that we created. It's called the Institute for Venture Science. And the idea is to fund promising ideas that challenge conventional thinking and therefore may bring scientific revolutions. If you've tried to think about the important scientific revolutions that have occurred in the past 30 or 40 years, I think you'll be hard pressed. If you think of a revolution that's a, I don't mean technological revolution, but scientific revolution, equivalent to say uncovering the genetic code in the mid-1950s, splitting the atom in the 1940s, of that scientific revolutions of that ilk, it's really hard to find them. And one of the reasons is that the scientific establishment is ultra conservative. They don't entertain revolutionary ideas. So those with revolutionary ideas are stuck because they can't find money to pursue their ideas. And that's what this institute is all about. And we've asked for pre-proposals. We got 200, more than 200. We carefully vetted them. We got 15 full proposals. And from those, we chose 5 exciting projects that I think if they're funded, if they work out, will change the world, will create scientific revolutions. And of course, the challenge right now is getting money. And we're looking for donors, people who have done well in their careers and would like to donate, give back to an organization that promises something that will be powerful for the future of humanity. So I think I'll stop there and just show the book that you've already seen. Thank you very much for showing the book. Got a nice cover and lots of cartoons. And what I've talked about, much of what I've talked about is shown in greater detail in the book. So I think I'll stop here. And I'm not sure, Nikolai, of the format of this, whether we quit or someone else starts or there are questions or whatever, but I'm, whatever you decide, boss.
Thank you so much, Jerry. Always a pleasure to hear.
Thank you.
Your thinking and your boldness, and yeah, you really remind us all of how science should be, and it should be a journey of discovery and fueled by curiosity and a sense of adventure. So
thank you for your kind words. Yeah, it's always fun to present this stuff because I'm so excited about it. It's all over the place, and yeah, okay.
Gerald, I have a question. Thank you so much for presenting.
Sure. I hope I have an answer.
I'm really fascinated about the human body and what water does, and you've explained it beautifully, and with what it does in the with the easy water. And I'm mainly really interested in how food reacts, the food we eat, and what types of food, and how we absorb that through different types of food. If there's a difference, have you?
Well, okay. I apologize because this is not an area of my expertise. I eat it, I enjoy it, and I've been told that I have to add vegetables, or a lot of vegetables, in order to preserve my health. But I'm not an expert. I actually, though, think I have a speculation. This is not written down, but I think that electrons are very important, and you know, a lot of stuff has negative charge, and I think that the food that we eat also mostly has negative charge, just like we have negative charge, and negative charge is really important. And we're full of it. All our cells are negatively charged. Some of the students that have been in my lab have tried to measure the electrical potential of the body, and it seems to be really negatively charged. And the conclusion that we drew on I should say evidence that is scant. We haven't done this extensively, but we're negatively charged, and the more negative we are, if you'll pardon the expression, the healthier we are. We need to pump negative charge into our body. And somehow the light can do it, because the light builds EZ and creates negative charge. And the positive charges we dispel, and we dispel them, for example, when we breathe, because the water that we breathe out is full of protons. It's low pH if you measure it. And so we get rid of positive charge that way. We also get rid of positive charge by sweating, because the sweat contains pH. And sometimes by urination too, because often the urine is low pH. So the body tries hard to get rid of the positive charge and maintain the negative charge. And the more negative charge we have, the more EZ we have. And the body absolutely needs this EZ to function. It's central to all function. So the food might actually act in the same way, because the food itself is typically negatively charged. And when we eat the food, we get this negative charge. So Albert St. Georgi remarked once that there's something wrong about current thinking, because he will eat something, he said, and the energy that he gets appears within a few minutes, like eating sugar, for example, and it doesn't require all the time of going through the digestive system, through the stomach, through the small intestine, and getting back. which requires at least tens of minutes, he feels the effect of the food very quickly. And so the question is, what's going on? And one speculation is that since the food has negative charge, as soon as we swallow the food, we get this negative charge. And the negative charge spreads rapidly around our body, fills the regions where we don't have enough negative charge. And this negative charge builds easy water. We have demonstrated that in the laboratory. So this is, I repeat, a wild speculation that it might be that it's the negative charge that's contained in the food that's really the most helpful for us in getting our energy.
Thank you.
I hope that answers your question. It's a speculation.
A follow-up question on that. Thank you for a beautiful and inspirational session. And I have a question about why. Have you thought of why it takes 1 hour for the natural flow in the blood vessels to stop after death? What is happening during that hour? What is like? Could that be a is it too much resistance when the heart stops, or is it that the radiation stops to function for the EC?
That's a good question, and I must admit it's a question I've never really thought about, because the implications of what you suggest are really profound. It means your heart stops beating, but you just go on living forever, right? And typically we don't. You know, if you, so again, pure speculation, but it's a really interesting question. I guess you need enough easy water to function, and all the processes that go on that depend on the blood flow. If you have only 10% or 20% of the blood flow that you have, they can't sustain all of these operations. And so, you know, you gradually go downhill. That's one option. Another possibility is you really need the heart to get the flow going, to drive it down into the capillaries, where in the capillaries, the mechanisms that I've been talking about are actually propelling or continue to propel the flow. So without that pressure from the heart, you don't get enough flow, and everything goes downhill. I mean, this would be an interesting research study to see what happens, but I guess I would think that all the processes in your body require full blood flow. And you know, if your blood flow decreases by too much, which would be the case if you eliminate the heart, and also the toxins that build up that your cells need to get rid of, it can't be done efficiently unless everything is working full bore. Those could be some of the reasons. Some of the other studies have shown these people, the Israeli group, if I remember correctly, it's at least 1 hour. Sometimes it lasted longer. In our own laboratory, we know how to keep it going longer, and maybe this is a clue to answer your question. I just thought of it. So the mechanism that is involved in producing the flow in the tubes is you have an EZ that builds, an annular EZ that builds just inside the tube, and right in the core of the tube are protons. And those protons are free and they repel each other. They're positively charged. They want to get out, and they can exit either one end of the tube or the other end of the tube. And then as they exit, they drag water with it, and new water comes into the tube, and the process gets perpetuated. So it keeps going, but as a byproduct of that process, protons go outside of the tube or the vessel, and they land somewhere. In our experiment in the laboratory, they land in the chamber outside the tube. So you can imagine the chamber gets progressively filled with protons. And we've measured that. We've confirmed that it's true. And if they do, it means that the protons inside, which have a great desire to go outside, to get out of the tube, no longer have that desire, because there are protons out there. There's not zero charge out there. there's positive charge out there. So the positive charge inside has no impetus to go outside. Same thing may happen inside the body, that you can't get rid of those positive charges. And so the flow that occurs gradually tapers off and stops, just the same way as it does in the laboratory. So that's my speculation as to what might be going on.
I have another question.
I'm here.
You had this this picture of a cell which is filled with easy water.
Yep.
And the orphan hydrogen, where did they go?
Well, the protons we're talking about, and the protons go out. So, good question. So every time the cell, you know, I didn't mean to convey that the cell always has this structured water. I pointed out really early in our conversation that there's evidence presented in my earlier book that the so-called structured water, which we now call EZ, fourth phase water, undergoes a transition. It's like a phase transition to ordinary water. And when that happens, everything inside the cell is fluid. And the protons that are inside the cell repel each other, and they want to leave. And so they leave. They leave the cell, leaving fewer positive charges inside the cell. And eventually those protons will escape our body. And I mentioned a few ways in which that can happen. And one way is through respiration. Every time we exhale, we get rid of protons. So eventually it works its way through the system, to the lungs, where exhaling gets rid of protons. And as I mentioned, also sweating, going to the toilet. My friend was actually measuring his negative charge, and he took a dump in the toilet. And apparently he told me that his negative charge increased. He got rid of positive charge. I don't know, that's not a publishable result, although might be. So we tend to get rid of our negative charge, our positive charge. And that positive charge, during the time the cell is activated, whatever cell it is, has an opportunity to leave the cell. And because the positive charges repel one another, they get out of the cell, and we lose them. So, so we keep losing positive charge and maintaining negative charge. And someone who's healthy is full of negativity, if you pardon the expression. The more negativity we have, the healthier the person. You know, it also says something for longevity, because one possibility is if loss of easy water and dehydration is a problem that afflicts us, including myself, it might be that if we can confer a negative charge, external negative charge to our body, we could then help to build up the easy water that's necessary to keep us going strong and healthy. I'm trying to convince my doctor. We'll see. We'll see how that works.
Thank you.
Oh, my pleasure. Okay.
Thank you so much,
yeah.
Jerry. Thank you, Jerry.
Okay, Nikolai, and
Word of wisdom.
I hope you people have a great rest of the conference. And
I want to say thank you for your talk, and thank you, Nicholas, to make it possible.
Yeah.
Thank you. And where are you guys from? At the people who just talked?
Yeah, we are from Ibiza. We work with the seawater company. And I was thinking what you said about the filter from the seawater.
Yeah.
Because you said sometimes there is a positive result and sometimes not.
Yep.
Because we observe also that different kind of water into the sea. So we can see there is the bulk seawater, and after what we call the marine plasma, who is the water which molecules are with a coherent state. Yeah. And thanks to Masaru Emoto, because he was saying that he couldn't find the structure into seawater. So I say, probably it's because you take the normal seawater. if you take marine plasma, it will change the structure. So we make the experiments. And of course, it changed completely the structure. So when you say that the filter sometimes when the easy water, it takes the solutes out, probably sometimes we can, I don't know, I'm just putting all these ideas, no?
Okay, I hear you. Yeah, well, maybe it's something similar. I don't know.
You see?
That's the molecular from the marine plasma, one of it, because it has a lot.
You mean that's a photograph from Emoto of the frozen?
That's a photo that Emoto made for us. This
okay.
is marine plasma that we harvest in Ibiza, and then we send to them, and they make the photo. Because he was not able to do it because he always found out many interference with minerals, and that's why it came the idea. Maybe it's because he's using just the water from the coast. And what happens if you use that water that is harvested in specific sites when there is a high concentration of plankton, and you harvest more deeper than the superfice, and then we send to him, and that's what appears. Then the photo appears.
Okay. How long ago was this?
5 years.
5 years ago.
He died about 5 years. So this was before his.
Yeah.
Yeah.
Exactly.
Yeah. Okay. Because I know there are lots of people. There are several people who are continuing with these kinds of experiments, and probably you know them. Are you living? Pardon me?
I've been traveled to Japan. I'm a voyage instructor also.
Oh, okay. Okay, got it. Yeah, okay. Okay, guys, thank you. Thank you so much. It was great to connect with you, and take care, and good luck with the conference. Okay.
You too. Thank you.
Thank you.
Okay. Bye-bye.
Bye.
Bye-bye.